and you should click that you got it on your screen probably. So we are about to start the second talk of the sloppy workshop on Oracle-based local search for pseudo-Boolean optimization by Jeremias Berg, please.
Thanks. In spirit of sloppy, I realized about 5 minutes ago I messed up the date, but that's maybe not the biggest thing here. All right, so this is going to be about some paper we published a year ago together with Marcus Eisner and Matti Järvisalo. And it's about an anytime algorithm that was originally proposed by Alexander Nadel for MaxSAT. So maybe the people who know MaxSAT have heard about this, but we hadn't heard this for PBO earlier. And I think there's sort of a lot of interesting connections. I was just telling you, this is a good example from where your improved propagation would make a difference. So the motivation here is we heard actually earlier about sort of optimizations and especially anytime solving, anytime optimization. Combinatorial optimization, I hope I don't have to convince you of its importance. Sorry. and diverse applications. And often, of course, the nice part about these solvers and proof login and everything is you can get optimal solutions, you can even prove them. But in many actual applications, maybe you don't actually care too much about if you actually have an optimal solution and you just want a good solution within. Instead, you have a limited amount of time to get a solution and you want to get as minimum cost as possible. So that's what I mean by anytime solving. And as I said, here we sort of take and one of the state-of-the-art algorithms in MaxSAT for this anytime setting and combine it with this very nice progress that has been done on conflict-driven Pseudo-Boolean solving and show that it actually improves. And it works out fairly nicely in this context as well. And at any time, if you have any questions, feel free to interrupt me. I'm sure Jakob will. My notation, I'll use this. We have a formula, which in the Pseudo-Boolean context is a set of constraints. We have 0, 1 variables or their negations, and we have an objective, a Pseudo-Boolean expression that we want to minimize. The goal is to compute an assignment that satisfies all of these constraints and minimizes the cost. Should be fairly straightforward there. And note that MaxSAT is a special case. You get MaxSAT from this by restricting these guys to just be at least one constraint, so clauses. Another important concept that I'll be using is what I call satisfiability under assumptions. So we assume that we can take a set of literals and then we can ask an oracle, a Pseudo-Boolean procedure, in practice rounding SAT in the context of Pseudo here, but it could also be a SAT solver. We can ask it for a solution that satisfies the constraints and also assigns all of the literals in this set to true. This is going to be important. And we also assume they can also tell us if such a solution does not exist. Practically any SAT solver you can think of will do this. Rounding SAT can do this. I think at the time when we were doing it, we sort of had to do minor hacks to the version of rounding SAT to actually get this to work. But nowadays it would be come out of the box. We extend this is nothing new, by putting in a conflict limit. We want to escape. What we're going to be doing is we want to ask it quickly for solutions. And if it cannot find a solution quickly, we don't really care. So we put in a limit saying you're allowed to try for, I think I have it on a later slide. I think it was 100, maybe a bit lower, conflicts, fairly low number. And if you haven't found a solution yet, just stop and then we'll do something else. So it's almost like unsat, but not quite because it's unknown. And this is sort of in the light of anytime we're doing anytime solving, we don't really care about the exact result. We just want to know it. So a very simple example, we want to put at least 3 of these guys to true and have some clauses and a nice objective function. If you want to find a solution that sets v1 and v5 to false, that can be achieved, by example, by this solution, which has cost 10. 6 plus 3 plus 1. If we want to ask it for a solution that puts v1 and v4 to false, that won't work because we have this clause here. And an optimal solution is, for example, this one that has clause 9. I think you can find a better one. I don't care. And we've already heard, well, I wasn't here, but Jakob, I'm sure, covered all of these exciting approaches that exist. You can do conflict-driven constraint learning, which builds on close learning, core-guided search. We have an implicit hitting set solver also, and solution improving search is the standard SAT and SAT, where you improve a solution by adding constraints in any time. Solution improving search is naturally a very anytime algorithm. You always have the best known solution that you can always give it to the user if they ask for it. Then there was fairly recently a stochastic local search paper, which is more like a standard type local search where you try to flip variables and literals and look for feasible solutions and are being very clever with your weighting schemes to escape optimums, very standard local search stuff. And now this Oracle-based local search, which has been highly successful in MaxSAT, and our paper is the first one to extend it to Pseudo-Boolean. You can, of course, convert to CNF, but I'm sure Jakob has told you all about why that is a bad idea, and you lose exponential power. And this more recent stuff is, at least to me, more exciting. And our approach can be described as a combination of solution improving search and Oracle-based local search. Essentially, we show how some extra tricks within the solution improving loop improves on overall performance.
You already promised that I would interrupt, so then I will interrupt. So just to say convert to CNF, that it's necessarily a bad idea is not true, right? I mean, sometimes it seems to be really good. These CNF-based solvers beat the pseudo-Boolean solvers because you add all of these extra variables that give you expressive power. But of course, the reasoning is weaker.
Yeah, that's true. It's a very open question. What do you want to do?
Yeah, it seems to be in some sense incomparable.
So very quickly, I'll go over these two building blocks, and then I'll go into how do we combine them. Solution improving search, as I hinted, is maybe the most natural idea one would think of when you want to convert a decision procedure to an optimization procedure. You find an initial solution. This can be done, for example, just by invoking your decision procedure on the constraints. As long as you have any solutions, it will find you one, and that will give you some kind of an upper bound on the cost, on the optimal cost. And now you add that and add a constraint saying, I only care about solutions that are better than the one that I already have. This is very nice to do in Pseudo-Boolean because it's a single constraint. This is also commonly done in MaxSAT, but then you have to, of course, encode Pseudo-Boolean into clauses, and that can get tricky and that can require quite a lot of memory. It sometimes works nicely, but sometimes definitely also runs out of memory. And then you go into this loop. Here we don't need assumptions. We just ask, give me a new solution. Since we added this constraint here, that solution, if there is one, will be better than what we already had. And as long as if you don't give it conflict limits, running SAT will at some point tell us there are no solutions, and now we know that the one that we have is optimal. But of course, the nice thing in our context is that we're constantly maintaining this best solution. So whatever time limit we have, we can output a solution. Unless it turns out, sometimes it turns out that even finding any solutions is very hard, but then what you're gonna do. Straightforward example on the same instance. You conceptually initialize your upper bound to infinity and your best solution to nothing. The first call will essentially be get me anything. Assume we get something like this. This has cost 3 plus 6 plus 3 plus 1. Let's see if I did it right. Yes, 13. You update your extra constraint. You invoke the solver again, and now it could get you many different things, but for the painting of this presentation, let's say it gets you the optimal one. And then in the final call, you'll get answered. And now sort of the nice thing to notice is we don't have to go improve by one, because often it turns out that the solver, if we had the bound of 13, the next solution is not, it doesn't have to be 12. It often is better, and then you can jump. A typical question I might get from people sometimes is, why don't you do binary search? Why don't you do lower bounding search? Like intuitively, the accepted wisdom is that unsat calls are really hard. satisfiable calls are easier. So hence this solution improving search, even though you might get sort of better bounds on how many calls you have to make with something like binary search, the solution improving approaches tend to work better in practice. And I've also actually run into cases where, especially in the context of MaxSAT, where I try to do clever things to improve the upper bound more and jump further, just to be beaten out by a SAT solver that learned something useful while doing the intermediate easy calls, and overall is still faster to get down than my clever heuristics to jump from bound 5 to bound 1 immediately.
So this is actually a question that came up yesterday. We discussed that the fact that is it important that the solver is stateful here, that you're going to keep that you're making repeated calls to the same solver, like compared to just suppose that you would just start with a clean slate plus the latest upper bound.
My intuition is that as long as you're doing solution improving search, keeping that state is important. If you're talking about some kind of hybrid that would be doing core guided search sometimes and solution improving search sometimes, there I don't keep the state. I have a solver that does core guided search and then does solution improving search afterwards, and there it's not worse to keep the state, unless it's not by much, but it's not definitely not better. So I tend to just reinitialize when going from this core guided. But the intuition is you're going from lower bounding search to upper bounding search, and now you're learning different kinds of things. Now then, the second building block, Oracle-based local search. Here I will make a difference between sort of traditional stochastic local search and this Oracle-based stuff. In traditional search, you have some kind of an assignment. Hopefully you want to keep it feasible, but sometimes it will not be a solution. Then the cleverness comes in sort of in which variable do you pick? You want to try to pick a variable to flip that would either satisfy more of your constraints or improve your cost. Often these solvers work in a way where they have a weighting scheme that initially tries to prioritize getting to a feasible solution and then tries to prioritize improving that solution and the choice is sort of in which variable do you pick. But sort of grossly simplifying, the idea is you pick a variable, you flip it, you check if you're feasible, and if you are feasible and you have a better solution, you update it. And then the challenge comes from how do you do this fast enough, and how do you escape local optimum? How do you make sure that you don't go in cycles, etc., etc., etc. And this works fairly well on many instances. The MaxSAT evaluations anytime track has had lots of stochastic local search solvers. There is one, which I of course did not cite on this page, but there is PBO-LS is for the same idea for Pseudo-Boolean optimization. But the contrast now to what we call Oracle-based SLS is you're only now looking at your objective variables, and your search is over the objective variables. So you have some assignment and some ordering of your objective variables, and now you want to start improving that. So here B3 is incurring costs, so let's try flipping it B3 to false. And now you use your Oracle, your SAT solver, your Pseudo-Boolean solver to check whether or not that assignment of the objective variables can be extended to a solution. And so essentially your neighborhood is now over different assignments to the neighborhood concept gets a bit funky in a way because your neighborhoods are defined by the objective variables, but then those can correspond to many different solutions. I'll have a more detailed example of this next slide.
Yeah.
But this is, yeah.
Why is B2 not appearing in the assumptions? Is it a typo? Or?
It's a typo, sorry. Yes, it should be. Yeah, this should be B2. Yes, typo. Thank you. So, yes, so the intuition here is we're forcing it to not incur cost on something. I'm checking if there's such a solution, and then we don't really care. Sometimes it happens that it cannot incur cost on something else, and that is nice as well. But we're sort of picking at least these guys you're not supposed to incur cost.
So the B1 should be
B1 should be B2.
Okay, thank you.
So let's look at the example. Same formula. We initialize And now this time we cannot we have to have some kind of a solution to begin with. So let's say we get this one, for example, by walking. We cannot initialize by from the empty now this time. And now we pick an ordering. And this is maybe the main, I'll talk more about this, but the main design choice here is which order are we trying these variables in? And this is sort of what defines your current search and your current neighborhoods. And now we'll start working through these objective variables in this order. And for each one, we sort of check in the current solution we have, is this guy incurring cost? Is it true? If it is, we ask rounding SAT for a solution that sets that one to false. And here it can give us, for example, this one. But in general, there's no guarantee anymore that whatever this result is, with solution improving search, it is always going to be better than your global bound. Here, it need not be, so you're checking every time. This time we got lucky and we went from 17 to 10, so we got a better solution. But then we stick with this order. So now we know that there exists a solution that sets this guy to false. But in the solution, this guy is still incurring costs, so now we want to check, can we put both to false in this order again? So the next query is going to be, can we do both? And here we can't, because of this clause. And this is also one of the design choices we had to sort of deal with, is what do we do if we get a lot of these unsets? Then that sort of tells us that this ordering is not the good one to go. So actually we do an early interrupt. If we get too many of unset calls in this ordering, we don't go through the whole thing. We just stop and go back and do some other ordering. It's heuristics, is anytime solving. We don't have to care about optimality. But here, for the example, since we couldn't put B4 to false and B4 was after B1, we're now fixing it to be true in the rest of the calls because we know we cannot do it, set it to false. So now we're asking B1 false, B4 true, and B2 false. The result should be SAT, and now we could get, at this stage, we could get the optimal solution. But of course, now we have no sort of guarantees on that. We don't know, we have no way of checking that this is actually the optimal solution. So what the algorithm will do is just keep on trying. Could we maybe put B3 to false as well? And then we get unsat. And this is partly why we also have to escape. Yeah, okay.
So all of these calls, importantly, will be run with a fairly short sort of timeout in terms of number of calls.
In practice, for this algorithm, it doesn't really matter if the result is actually unsat, if there is no such solution, or if it's hard to find. So if we have assumptions that lead to a long call, that's just as bad. So we just put a complete limit on these calls because we don't have to care about optimality. And actually, after publishing this paper, we've been talking a bit with Alexander as well, and we learned that there are two different ways that he does this in MaxSAT. What I just described is the so-called Mrs. Beaver algorithm, where the assumptions are the prefix of whatever ordering you're trying. Then there's the second algorithm that he calls Polo-SAT, where you're actually just trying the latest one and trying to always only have one assumption. So the intuition is you have more freedom to give to your solver. And he says that the heuristic is basically he has a very short conflict limit for this call. And then if that doesn't work out, he'll try this because this is more restricted and conceptually maybe a bit easier if you're fixing more. We didn't try this for the ECAI paper, but we're sort of running. Marcus is running some experiments on how to make this work in Pseudo-Boolean.
And what do you do if the first Polo-SAT call works out and like the second?
Then so you would first try can it put B1 to false, then you would try can I only put B4 to false, because supposedly the rounding set can still go well. Yeah, I can do both. There is the set of solutions here is larger than the set of solutions here. And if you combine this with the heuristics I'll talk more about, that sort of force the search to go to the same area, you often end up with the good solutions anyway. So you can there are some extra tricks to pull.
Do you keep track of the successful assignment in those cases? Because if the assignment that works for B1
Yes.
also needed B4 to be true,
Yes.
it wouldn't make sense to check for B4 true.
Yes. So the one of heuristics that you can do, and which is done, is whenever you get a new solution, you actually sort of anything that's already false, you shuffle, you put next in the ordering, so you're avoiding false. So if you get a call with B1 that says B2 and B3 to false, you'll just move them up, and then you'll jump to the next one that's actually being still incurring false. That is one heuristic improvement.
But sorry, a very naive question, but this upper bounding constraint is always there, or it's not there now?
This is the next slide. This is sort of Oracle-based local search.
Okay, so
yes.
there is no upper bound.
So now we're still on the building blocks.
Okay.
And I think the next slide is actually going to be exactly what we do now. And now we have this upper bounding constraint. So we tried this pure Oracle-based search that didn't really sort of work. But what did work is combining these two. So essentially, you can see it as a solution improving search that has this inner loop where it does this more restricted calls with more assumptions. So you have some solution, you put your upper bounding constraint, you shuffle, and then you do the loop. And then I just told you about, importantly, with a conflict limit on every single call. And the fail limit was what I was saying. If it turns out that in your current ordering of objectives, you get a lot of ansats or a lot of interrupted calls, then it's unlikely that will lead to a better solution. So you just early escape.
But now I don't understand. You say if the solution is better, it says somewhere in the middle of the slide, but it seems in the beginning you set F to F union best. So like how?
Okay, yes. So in practice, yes, sorry. So it will be better.
It will always be
Yes.
Okay.
That's a good point. This slides were more sloppy than I was thinking. The other sort of heuristic we have is the stagnation limit. If we've tried a certain number of orderings and we haven't been able to get here, essentially, we haven't been able to improve the solution, then we'll run without conflict limits or without assumptions, so a pure solution improving call, which is now, since we don't have a conflict limit, this will actually always get either one of these cases, either we will get a better solution or we'll know that we are at that.
So just to check, is it correct to say that the first you do for a limited time, you do Mrs. Beaver or Miss Beaver?
Yes.
And if for whatever reason you just decided, this just doesn't seem to be working very well, then you say, whatever, let me do standard solution improving search.
We'll do one call of solution improving search. Okay. And then we'll done with optimum or we'll get a new constraint here. Okay. And now we go back to trying.
Then you go
with Beaver.
So sort of your preference is always for the Beaver, but if it like fails, then you as a fallback you do just the same.
Yeah, the fallback, the main fallback is almost this remove the conflict limit. So sort of accept that, well, this seems to be hard, but now we have to let around it and actually just do it anyway. And now a bit on this, what are these extra tricks that you have to pull? As I already alluded to, the central design choice is here. How do you sort your objective variables? When you have one ordering, what do you do? And that is sort of the main driver of what kind of a search you do. And in this paper, we did experimented with a number of different things, and the thing that worked best is, I would call it like a bucket shuffle. The idea is that you partition. You order your objective by weight, so you want to have high coefficients. In the same grouping, then you group your objective coefficients in a way that each group contains the variables that have similar weights. So the variables with high weight will be in their own group, and the variables with their low weight will be in their own group. and then you shuffle these groups. So you're sort of shuffling the objective, but you sort of want to maintain some kind of notion of, well, the high weight guys should be close to each other in the grouping, and the low weight guys should be close to each other. And on every odd iteration, you just do this and then you reverse the list. And this is sort of corresponds to diversification in standard local search. So maybe we're stuck in a local optimum and now we want to do something that kind of doesn't make sense from the point of view of improving, but we want to go somewhere else. So example, with 2 buckets, you would end up with B4 or B1. I don't remember how we break ties, but this, I guess these two are equivalent. But buckets like this, we shuffle the buckets individually, and then we combine that to get the order in which we want to start trying.
I don't understand the first point, the previous that to say that you will start with ascending order of cost. Is that one example or?
It is implicit. Yeah, okay. So what I mean is just the partition is done so that the cost. So implicitly we sort them to be, well, it happens to, yeah. So
Ascending order of cost.
yeah.
So you will prioritize sort of the cheap and easy, the most likely to be possible assumptions. You make them first.
Yes, except for this.
The first time around, and then chaos reigns, I guess.
And that has to some extent to do with the second one of the, so you want to sort of have the decision procedure simulate a local search type thing. So you want to, if you have some notion of a best solution, and we're going to guide variable selection to go into that region. And now it might be easier to get a slight improvement in that region by flipping a low cost one rather than getting a big improvement. So iterative slight improvements are preferred and seem to work better in practice. So the 2 heuristics of the decision procedure that we mess with and that Alexander messes with in MaxSAT are activities and polarity selection. So which variables should rounding set try decisions on first, and which polarity should it try first? We have 2 different modes. One is for what do we do in the first call where we don't have any solutions yet. And the second one is then what do we do inside the Mrs. Beaver. So in the first call, we want to make it try variables of objective variables of high cost first, and we want to make it try not incurring cost on them first. So try those. So this is bump the activity scores. I think there are people here who would know better, but some visit like scores on those variables proportionately to their weight, and fix the polarity checking to be false if true incurring cost. This is the sort of idea. We want to find the first solution. Hopefully, that's the first solution could be as good as possible, but we don't want to put hard limits on the solver yet.
So just to note that this is a place where you really need to go and hack your black box because it's not doing this for you. So, but suppose you had like an interface that would allow to give like a bump factor for each variable, and you'd maybe like a polarity indicator. Are we doing phase saving or do I have my favorite phase? Then you're saying for all objective variables, I want to fix them to the non-contributing phase. Yeah. And maybe non-objective variables get a bump of 1, and objective variables get a bump of, I don't know, the coefficient +1 or something.
This is also the place where you have sort of, in the end up in the wind. So coefficient times a magic constant, and then you have to find the magic constant, and that is somewhat annoying to do, but there's no formal justification for what exactly you should choose, but it's a lot.
But you've been playing with the magic constant to see what.
Not too much. We try not to do it too much because parameter tuning is not that interesting. But of course, we want to try to see a bit if it does affect, how much it does affect, doesn't matter. And it does matter a bit, but we didn't go into extensive detail. If you're interested, I guess you can run Slack or something to find.
Good point, yes. Mm-hmm.
In the internal loop, we do solution guide-based phase saving or whatever you want to call it. So we have, as I said, we have some notion of what is the best known solution we have. And we'll force the polarity selection to be exactly the same as that solution. So the intuition here, I mean, Stucky and Emil wrote a better intuition paper. The intuition is there is this region of the search space where the best solution that we now have is let's go there and let's try to look first close by to that solution. So their paper is called something like Stimulating Stochastic Local Search in CDCL.
So this is interesting. So let me just check. So what you're saying, do I understand correctly? Like for objective variables, I don't care about the incumbent solution. I just want them to be false.
In the internal loop, we fix. This is the difference between MaxSAT and PBO. In PBO, I think we have it in the paper. In the internal loop, we will fix every single variable, regardless. We don't care if it's an objective variable or not to match the best solution. In MaxSAT, I know that Alexander does exactly what you say. Objective variables always. I don't want cost. The rest according to the best solution.
So I don't know if this has a name. For now, I'll call it just incumbent phase, maybe. But there would be like two flavors of incumbent phase for every single variable. Set it to the value that it had last when you get to choose on it. And incumbent plus improving objective would be, well, except for the objective variables, I always try to set them to false. And you're saying this is not obvious which of these two would be best.
In MaxSAT, TT in OpenW Inc. does this second thing, incumbent plus improving. I think I'm 90% sure that in this paper we did the first thing, every single variable to match the best notion.
And there will be no overwriting of this phase. This is like a fixed phase.
Not in the current version. There's no reason you couldn't. And this is another thing where you could sort of maybe get into details and try 15 million.
Oh, so you're describing the initial phase for the
initial solution substitution refers to when we don't have
in the Oracle for like you start with this phase, but will you start when you start seeing unit propagation? Will you overwrite the phase, or have you fixed the phase?
We have fixed the phase.
You fixed the phase.
Yeah.
So you will not change it.
No.
Okay. Cool. Great. That's what I.
Yes. Mm-hmm. There is a paper from Alexander where he tries different ways, essentially all of these things in MaxSAT. I can't remember by heart what the conclusions were, but it is sort of MaxSAT has been studied more extensively than what we did here. Any more questions about the actual algorithm before I show you numbers? So we implemented it on top of rounding SAT at the time and compared it to this LSPBO, which is a pure stochastic local search. Rounding SAT, which I'll acknowledge here, is not designed to be at any time, but still did fairly well in an anytime setting as well. And these last two are the same code base, but removing this Mrs. Bieber phase. So how does our own solution improving search in this code base work? And what effect does this Mrs. Bieber loop actually have? And the plus refers to this polarity selection and activity bumping. So it's sort of an ablation study of what do these things actually do. The main metric we used is the same as we used in the evaluation, anytime track. So for any instance, copy slides again. For any instance, we have some notion of what is the best known cost that we can find. If an exact solver is able to solve it, nice, we'll use that. If not, it's the lowest cost of the anytime solvers. And then we divide that by whatever cost the solution that your solver got. And this will be a number between 0 and 1. 1 means you matched the best known solution. 0 means you didn't find a solution at all. That also did happen. So you want to be as high as possible. These are the magic numbers that we fixed for this experiment. Number of buckets, which divide an objective into 8 parts and shuffle those parts individually. The nation limit was quite low. So as soon as we tried a single ordering in the Mrs. Bieber loop, that didn't improve. It turned out to be better to just do a solution improving call. Okay, this is way lower than I thought. Conflict limit, and this is sort of where I want you to implement propagation better. I think Yonder uses a conflict limit of 100 or even a slightly more in CDCL SAT solver. In rounding SAT at the time, that took too long. We couldn't use that high. And the fail limit referred to how many, in a fixed ordering, how many objective variables are we willing to try and fail on, get unsat or interrupted before we abandon that ordering.
Just to point out that you can also play with the rounding SAT conflict analysis. For instance, if you turn on more aggressive weakening and so on, the conflict analysis will be way faster.
Yeah, if there's a nice interface that we can use to find all this thing.
I think there are probably options for this. I'm not sure about the documentation, but the code is its own documentation, right? It's open source. So could you elaborate what the problem
I
is?
have heard nice things about the rounding that code, which is completely understandable by anyone. No, I'm not. This is a place where I'm not gonna stand here and place all blame on rounding SAT. We didn't we were using it very much as a black box and found the names that refer to stuff that we could recognize from SAT.
Do you know if you're running it with linear programming integration or not?
I think so. I will check the paper. We just took the best performing ones. I would say if it's on by default, then yes. If it was on by default.
You need to compile.
Probably you need to compile with it, but if you have compiled with it, then it's probably on by default, I think.
Yeah,
which might not be a great idea for, at least according to what the slide said yesterday, I think. People present in the room had a more active state of mind than I do. I believe I said something like, reading from the slides, that LP integration was not so great for decision problems. So this is something that you might want to switch off. No, I think I definitely better unit propagation. Any time of the day, it would be super exciting. So this is not to.
And I'm not. Rounding SAT is great. I don't have. I pointed not to say that it is our results are only because of rounding SAT. There's stuff we could do as well. But just to as I said, CDCL SAT solver, so he uses 100 as a login, and we're stuck with 20.
Can you remind us what was the difference between the stagnation limit and the fail limit?
So stagnation limit refers to how many times are we willing to do a full ordering and not improve on the bound before we're going to do a unlimited solution improving fault.
Okay.
Fail limit means within an ordering, how many variables are we willing to try and fail on before we
declare stagnation?
Yes, essentially with these numbers, yes.
Okay.
But maybe this comes from the time limits. So
just to understand, but if you had fail limit 10 and stagnation limit 2, then you would start with one order.
If we fail on 10 literals, we throw that order away. We take a new one.
But that means in particular you never do. Okay, but then when you get back to Mrs. Beaver after the second full call,
then
do you then know? Do you start with a complete? You still have your bucket order.
The same one, but when we do a new bucket order. So this shuffle them again, except if it's an odd iteration, we'll reverse.
But then I don't understand. Yeah, is reversal ever happening? Because if you only have stagnation limit 1, then you will always be sorting in increasing order and do shuffling within the bucket.
Yeah, okay, well, there's a separate counter. So how many times have we tried the Mrs. Beaver loop into?
Okay, yeah. So, okay.
But that is also, we tried the different numbers, and these are sort of connected. If we can do higher conflicts, then maybe we can do more stagnations before, etc., etc. Here are numbers. This average score over the same set of benchmarks, if I remember correctly, that we used in the IHS paper. Nowadays, we would hopefully use the competition benchmarks. And they were surprising to me. It's quite a lot of benchmarks on which we were unable to find any solutions at all. So they can be quite hard. And as I alluded to, rounding SAT, even though we ran the core guided optimizer as at the time best performing by the other paper that existed, it still did quite well in the design task setting as well, which is surprising if you know what core guided search is designed to do. It is definitely not an anytime algorithm.
How many instances did you have in total?
I should have written that. I can check that. We do have that in the paper, but I don't remember. Sorry.
And can you help us? Like, I'm not familiar with the MaxSAT number. Like, for instance, 0.84, 0.83. Is that a meaningful? That's like a clear difference, or is it like a noise or something in between?
The MaxSAT evaluation differences were all in. I don't think there were any difference or meaningful differences on the best solvers in the second decimal, so they were all in the third. So the second decimal is already quite significant here.
Okay.
And the parameter choices that we tried, the differences were quite small. So I think most of them affected only the third decimal onwards, but a few of them.
So in particular, for instance, the difference between SIS plus and SS, that's a fairly like a massive thing.
Yeah, so this heuristic thing so the way in which I see it is during this variable activity bumping and phase saving, that will already improve, and then doing this Mrs. Beaver on top of that will give you a bit more. On quite many of the domains that we had, differences between these solvers were quite small. Here are the ones where there's more than the first decimal in difference. All of these numbers are in the paper. For the stochastic local search, we observed more domains on which differences were higher. Maybe the more interesting part is this. So this is now the same code base with the solution improving search, with the variable selection and polarity, activity bumping and polarity selection, and then this combination. And this sort of shows you that almost like the main driver is this variable, as we said, playing with the heuristics of the decision procedure will increase your performance more, but then you can do this Mrs. Beaver to do even slightly better.
I realize now that one really interesting thing would have been to see the effect of your changed bumping, but I guess you don't have that, or no?
Not individually. It is sort of in this. So this
that's part of.
This is polarity selection and activity bumping.
Okay.
Yeah, I don't have it separately now. And then finally, this point I want to make here is mostly that, as with much everything else, the answer to almost any question of what did it make a difference is, well, it depends on the instance. So this is comparing with the stochastic local search on the left and the rounding SAT on the right, and as you can see, it tends to split. So if you have a specific Pseudo-Boolean problem you want to solve, don't blindly stare at the competition results and take the best performing solver, because it might actually make the solver that was 5th or 6th might actually be the best one for your domain.
So you're saying looking just at one solver get a higher count than another, that is not, these might be completely different sets as we did. Oh.
These are, of course, we tried our best to make a sort of heterogeneous balanced benchmark set, but still, if you're interested in a specific problem, your results might vary.
Which can be construed as like, if you want to build a solver that is actually useful, then you shouldn't optimize for the MaxSAT score, but you might want to support several different options and make them visible with options.
Yes.
And so that, once I have my particular problem that I really care about, I'll pick whatever combination is good for that.
Yeah, once the person that comes along that has a specific application in mind, they might pick your solver that does fairly well on this balanced set of benchmarks, and then they can fine-tune it to make it work on their problem. So definitely giving options to users, giving an API that's nice to use, that's well documented, will have a significant effect on how many people will actually want to use your solver. Anytime constraint optimization is super important. we heard from previous talk that we can learn in the PBO community from MIT people. I would say we can also learn, and we have learned from the MaxSAT people. And at the time of writing, at least, the careful combination of this Oracle-based search and this standard solution improving search was state of the art in anytime PBO, while also being orthogonal with the other approaches to some extent. The link is very ugly, but the point is the solver is available, and if you want to try it, you can. And when all of these nice things to running SAT are implemented, we'll be sure to add them to this one as well. Thanks very much.
So thanks a lot, Jeremias. Do we have any questions? We had some during the talk already, but more questions is always fun. So one question. Could you say anything about, like, comparing this to the standard, more like just, I mean, there's this local search where you just do this flipping and you try assignments to, like, basically complete assignments and try to flip and do things. Would these like, should you, again, are you saying that your approach and this sort of quote unquote standard local search approach also has like complementary behavior?
Yeah, it wasn't that.
So that you should, but then the answer is like, should you implement a solver that switches between both and then you'll make a killing?
I mean, this is what has been going on in the MaxSAT community. Most of the anytime solvers that you see in the MaxSAT evaluation, when they say something like NUWDLS, if you read the description, it will say we do stochastic local search for X seconds, and then we switch to TT open WVPO, which is misbehavior. So yes, there it works.
But then, will they then switch back and forth between stochastic local search and Mrs. Beav, or it's like?
I haven't looked in detail, but based on what it says in the description, I think no, but I cannot be sure. But this one. This is our approach with the stochastic local search. So yes, it depends on the instance.
Do you have any impression of the type of instances this works best? In a sense that, I've observed sometimes that there are instances in which there's kind of a continuum of solutions of, one by one, as small as possible. Whereas there are some instances in which you have kind of 6 different solutions, and that's going to be it.
Well, my intuition is that compared to a standard solution improving search here, you're sort of trying to do smart guesses and fixing more of the variables. So maybe that will work better in a setting where not every single assignment objective variables will lead to a solution, but only a few. And now you're trying to sort of guess and help the solver along to find those. While if you have sort of, I can put the objective in any way I want to, and I will maybe get a solution. If it's above the cost, then maybe standard solution improving search is better, because as soon as you find even one, you're done with it.
So then let's thank Jeremias again.